All right, guys, so quick review of, I guess the review questions. Number one, the population of a town is increasing by 632 people per year. Since it's increasing by a number, not a percent, we know that it's linear growth. And what will the population be in 4 years? It's starting out at 1,400, and it's increasing by 632 people every year for 4 years. So I can either add 632 4 times, or I can just times it by 4 and then add it to the 1,400. Either way, you come up with the same answer. Number two, during the worst periods of hyperinflation, the price of food increased at a rate of 30% per month. State, because it's going up by a percent, that is exponential growth. And then it wants us to say what the food bill will be, 3 months later. So if your food bill was $110 in 1 month, wow, you eat super cheap. But after 1 month, so we start at 110, and it's going to go up by 30%. So there's a couple of ways that you can do that. You can find 30% and then add it, or you can just times it by 1.3, which is 130%, and you're going to get the same answer. And when you get your answer, so if I go 110 times 1.3, that means my new price is $143. But the next month, it goes up another 30%. So I'm going to take 143 and times that by 1.3. So if I go back times by 1.3, I get 185.9, which is $185.90, but I've got to go up one more time. So I'm going to times that by 1.3, and I get $241.67. So your final price is going to be $241.67. You've got to go up by the percentage each month and then add them up. A king in ancient times. This is the chessboard one. There's 64 squares. He starts with, 1 grain of wheat, right? And then it's doubled. And it wants us to know what is the weight in tons of all of the wheat that will be placed on the first 48 squares. So the first thing that we need to do is figure out pounds. So it says, assume that each grain of wheat is 1/7,000th of a pound. So if I start with 1/7,000th, and I'm going to times that by my number of grains. I've got 2 to the 48 minus 1 grains of wheat. So I'm going to start with 2 raised to the 48. I'm going to minus 1. That's how many grains of wheat I have. So if I times that by 1/7,000, that's going to give me my pounds. But it doesn't want it in pounds. It wants it in, what does it want this in? Tons. So 1 ton equals 2,000 pounds, right? Right here, 1 ton is 2,000 pounds. So if this is my number of pounds, if I divide that by the 2,000, it's going to give me tons. So 20105,355. Wow. And how does it want this rounded? Use scientific notation, round 6 decimal places. So 2.010536. So 2.010536 times 10 to the, I didn't count how many times I moved it. 1, 2, 3, 4, 5, 6, 7. Times 10 to the 7th power. That's how many tons of wheat the inventor of chess would have after 48 squares. Okay, a leprechaun places a magic penny under a girl's pillow. The next night there's 2 magic pennies, and this repeats. So we're doubling every night, okay? How much money will the girl have after 22 nights? So for this one, I'm going to take 2 and I'm doubling 22 times. So 2 to the 22nd power, if I do that mathematically, 2 to the 22nd power is 4,194,304. So 4,194,304. That's how many pennies I have, but it wants to know how much money the girl has. So I'm going to times that by the value of a penny, 0.01. So I take that, I times by 0.01, and that gives me 41,000. So she would have 41,000, and we're going to round to the penny. So 41,090. Let's see, $41,943.04 is how much money she would have after 22 nights. That's a lot of money. The initial population of a town is 3,000, and it grows with a doubling time of 10 years. What will the population be in 8 years? So remember, to do our population growth and all of this doubling mess, our new value is equal to our initial starting value multiplied by 2 raised to the little t over big T. And remember, big T is the number of years it takes to double. Little t is the number of years. So if we start at 3,000 and it doubles every 10 years, so I'm going to times that by 2 raised to the 10 goes on the bottom because we're only going 8 years. So it'd be 3,000 times 2 raised to the 8 over 10. So 3,000 times 2 raised to the 8 divided by 10. So 5,223. So come on, pen. 5,223 people. The half-life of a radioactive substance is 50 years. So remember, half-life, instead of doubling, it decreases. It cuts in half. If you start with the same amount of this substance, what fraction will remain in 150 years? What fraction will remain in 200 years? If you start with the same amount of this substance, what fraction will remain? So we're just looking for our half-life factor, okay? It doesn't tell us what we're starting with. It just wants to know what is the factor that we're going to be reducing by. And to do that, you take 1/2 and you raise it to the little t over big T. And remember, big T is your doubling time and little t is your years. So I'm going to take 0.5 and I'm going to raise it to 50 divided by, nope, not 50 divided by, bad math. Come on, eraser. 50 goes on the bottom, my doubling time goes on the bottom, and on the top is going to be 150. So 0.5, that's basically 0.5 raised to the third. So I do 0.5 raised to the third power. So 0.125. And it wants this simplified, so it probably wants me to turn that into a fraction. So if I do math, enter, enter, I get 1/8. And what's going to remain in 200 years? So 0.5 times 200 divided by 50, which is just 0.5 raised to the fourth power, which is going to be 1/16. Or put it in your calculator, you'll get the same answer. Okay, number 7, the half-life of a drug in the bloodstream is 14 hours. What fraction of the original dose remains in 48 hours? So remember, when it says what fraction, it's asking you for the half-life factor. You don't have to actually find the new amount, you just have to find what fraction of the amount. So that's our 1/2 raised to the little t over big T. So my 14 hours is my doubling time. So I'm going to do 0.5 raised to the 48 hours over 14 hours, which again is just 0.5 raised to the third power, because 48 divided by 14 is 3. So that's going to be 1/8. Do not round until the final answer, then round to the nearest hundredth. So it might want 0.125. And how about 72 hours? Again, just like the last problem, 0.5 raised to the 72 divided by 14. That's going to be... Oh, you know what? It's not 48. That's not exactly the third power. Let's do 0.5. Let's go ahead and put that one in. So 0.5 raised to the 48 divided by 14 is going to give me a decimal, 0.0928. So 0.0928 round to the nearest hundredth. So that's going to be 0.09. And then in 72 hours, we're going to do 0.5 raised to the 72 divided by 14. And that's going to be 0.028. 0.028 round to the nearest hundredth is going to be 0.03. Is the fraction that remains. We don't know what amount that is. We just know that's the fraction. That's the part that remains. Use the approximate half-life formula for the case described below. Discuss whether the formula is valid. So we're using the approximate half-life formula. And remember, that is where we say that the half-life is approximately 70 divided by the percent. Okay? So urban encroachment is causing the area of a forest to decline at a rate of 4% per year. What is the half-life? So we estimate that it's approximately 70 divided by 4. So I would say 70 divided by 4 is 17 and a half. So I would say that it's about 17 and a half years. What fraction of the forest will remain in 20 years? So I go back to my formula. This is basically, I'm using this as my double, or as my half-life factor. So I go back to my original formula that we used in the last problem. So I'm going to take 1/2, and I'm going to raise that to the little t, which is 20 years, divided by the big T, which is 17.5. So if I go 0.5 raised to the 20 divided by 17.5, I get 0.4528. So 0.4528 round to the nearest thousandth, so 0.453. Be really careful as you round. Is this formula valid? Now remember that the half-life and the doubling estimate is only valid if you're dealing with percents under 15%. So I would say yes, because we're only dealing with a 4% growth, this formula is valid. It's not exact, it's an approximation, but it's valid, okay? All right, number 9, using an annual growth rate of 1.3% in a 20-year period for a certain population, find the approximate doubling time, and then predict the population. So again, we're approximating the doubling time. So I'm going to take 70 and divide that by my percent, 1.3%. So 70 divided by 1.3 is 53.846. Round to the nearest whole number, so we're going to say 54 years. That's our approximate doubling time. Then predict the population in 2050 if we started at 5 billion. Okay, so I started at 5 billion. I am doubling, so I'm going to take 5 billion times 2 raised to the little t. Now my little t is, let's see, we're going from 2000 to 2050. So my little t is 50. We're going over 50 years. And my doubling time, we said, is about 54 years. So 5 times 2 raised to the 50 over 54. So 5 times 2 raised to the 50 divided by 54. Enter 9.4995. So it's approximately 9.4995, and it wants me to round to the nearest tenth. So I would say about 9.5 billion would be the new population if I started at 5 billion, okay? Which makes sense because we've almost reached the doubling time, so we're almost twice as much. All right, number 10, right? Number 10, the following table gives the birth and death rates for 4 countries. Country A's net growth. So 1985, country A had 14.6 births minus 11.8 deaths per thousand. So you're going to do 14.6, you're going to minus 11.8 and get what? 2.8? Per thousand. Country A's net growth in 1995. So 10.8 and 11.4. So I'm going to do 10.8 births minus 11.4 deaths. That means I'm actually getting a negative 0.6 per thousand. So that means I'm going down. My population growth, I'm getting smaller in 1995. In 2003, I was at 9.3, and my deaths were at 11.1. So I'm going to do 9.3 minus 11.1, which is going to give me a negative 1.8 per thousand. So choose the best prediction about country A's future based on the trends in these 3 years. Well, it looks like as time goes on, my population is actually decreasing because now my population growth is in the negatives. Use a growth rate of 1.2% to predict the population in 2058 of a country that in the year 2006 had a population of 300 million. Use the approximate doubling time formula. So approximately 70 divided by my percent, 1.2, is going to give me my number of years till I double. So I'm going to do 70 divided by 1.2. and get 58 and a third. So it's approximately 58 and 1/3. That's my doubling time. So if I take my initial population, 300 million, and I'm going to times that by 2 raised to the little t. Now I'm going from 2006 to 2058, so that's 52 years, divided by my doubling time, which was 58 and a third. So 300 times 2 raised to the 52. So 300 times 2 raised to the 52 years divided by, I'm going to go ahead and steal my answer from before that, 58.3. And I get 556.5. And it wants me to round to the nearest whole number. So 557 million is going to be my predicted population in 2058. Okay, number 12. State whether 2 variables are related in a way that might be described by a function. If so, identify the independent. You walk through a used car lot and list the price and model year of each car that you see. So we're comparing the price and the model year. So could those be related? I would imagine an older car is worth less money, so the price is going to be cheaper. So I would say that it can be described by a function. Not that one. It can be described, the dependent variable is the model. Well, I think that the price depends on the year. So the year is independent and the price is dependent. So the dependent variable is the model and the independent variable is the price. That might be the right one. The situation can be described by the dependent is the price and independent is the model. Nope. Wait, isn't that what we just said? The dependent is the price. See, we marked the wrong one. B, the dependent is not the model. The dependent is the price. So we know it's not B. C is actually the one that we probably want. I read that backwards. The dependent is the price. We said that right here. The year is independent, the model. There is a dependent variable, but no independent variable. That doesn't make any sense. So C is your best answer. Okay, 13. In the following situation, same thing. Is it a function and how does it relate? You're purchasing a new car and you want to know how the money spent on gas depends on the car's miles per gallon. So if your car has a higher mile per gallon, you're going to spend less money on gas. So, and it tells you right now that the money depends on the miles per gallon. So yes, it's a function. The dependent is the money. The independent is the miles per gallon. So dependent, let's see, the dependent is the money. The independent is the car's mileage per gallon. Yes. This one said there is a dependent but no independent. Not true. The situation can be described by a function. The dependent is miles per gallon. No, the miles per gallon was independent. It even told us that in the problem. Okay, 14. Write a short statement that expresses a possible relationship between the variables. Travel time from Denver to Chicago, average speed of the car. So how does this express? Well, as the time to drive increases, the average speed decreases. I don't think that's the way that it works. As the average speed of a car increases, the time it takes to drive also increases. No. As the average speed of a car increases, the time to drive decreases. That sounds right. As the time to drive increases, the average speed increases. That one's also not correct. So even though, and this is going to be hard because A is almost an explanation as well. It just goes backwards. A is saying that as the time to drive increases, the average speed decreases, but it's actually the speed that is affecting the time. So it does matter which direction you go. Okay, 15, consider the graph. Identify the independent and dependent. So the independent variable is the one here on the bottom, so years. Dependent variable is the one on the side, so that's the population. The domain of the function, it goes across the bottom. So from 1950, so it's the years from 1950 to a maximum of 2000. The range is the population, and it goes from right about here. So it goes from, let's see, round to the nearest integer. So I'm going to say that rounds to 2 billion. It goes down to 2, and we go up to about 6 billion people. So I look at the lowest amount and the highest amount. Choose the description below. The function shows that the rate of increase in population, wow, that printed out ugly. So this is saying that as the years go by, the world population increases. So as the years go by, the world population increases. And I don't know which one of those messy things says that right there, but one of them does. Okay, 16. The following situation involves a rate of change that is constant. So that means we have a linear graph because my rate of change, my slope stays the same. The water depth in a lake decreases at a rate of 10 inches per week. Oh, well, I drew my line the wrong way because we're decreasing. So this would be my depth of my water. This would be my weeks. So the water is decreasing as the weeks go by because of evaporation. How much does the water depth change in 4 weeks? Well, if it goes 10 inches, if it goes down 10 inches per week, that's negative 10 inches times 4 weeks. So negative 10 times 4 is negative 40 inches. How much does the water depth change in 4 weeks? Am I missing a question here somewhere? Oh, write a statement that describes how one variable changes with respect to the other. Okay, I did miss a question up there. So time varies with respect to water depth. No. The water depth varies with respect to time. Yes, the depth is changing as time changes at negative 10 inches per week. That looks pretty good. Time varies with respect to water depth. Nope. The water depth varies with respect to time with a rate of change of negative 10 weeks per inch. No, it's inches per week. Be careful about the units right there. So the water depth has decreased by 40 inches. How about after 15 weeks? Well, the depth has decreased by 150 inches, right? Because we're going down 10 inches for 15 weeks, so that's negative 150. So the water depth has decreased, that's what that negative tells me, by 150 inches. Okay, 17. The following situation involves a rate of change that is constant. This looks almost exactly like what we just did, right? You run along a path at a constant speed of 2.6 miles per hour. How far do you travel in 2.6 hours in 3.3 hours? So you're running along a path at a constant speed. So you are going miles. Whoops. You are going, your hours are across the bottom. Your miles are dependent variable. So time varies with respect to distance. No. Time varies with respect to distance. No. The distance varies with respect to time at a rate of 2.6 miles per hour, not 2.6 hours per mile. What is the distance traveled after 1.6? So you are going to take 1.6 hours and times that by 2.6 miles per hour. So 1.6 times 2.6 is 4.16 miles. That's how far you went. What is the distance traveled after 3.3 hours? So 3.3 times 2.6 is 8.58. So you do 3.3 times 2.6. This is your time multiplied by your speed. Okay? 18. Another linear function. The cost of leasing a car is $1,100 for the down payment and a processing fee plus $330 per month. So $1,100 down plus $330 per month. For how many months can you lease the car with $3,350? Okay, this is an interesting question. The independent variable is time, and the dependent is the amount paid. So does the amount that you drive the car depend on how much money you have? Yes, it does. So that looks okay to me. The independent variable is the amount paid, and the dependent variable is the months. Yes. Did I read the other one backwards? Oh, I did read that one backwards. See, I did that twice now. Read these carefully. The independent is the amount that you're paying, and the length that you can drive the car depends on how much you pay, right? So if I have $3,350 and it's going to cost me $1,100 processing down payment and then $330 a month. So I'm going to minus 1,100 because I'm trying to figure out M. So minus 1,100 gives me 2,250 equals 330 M. Divide by 330. So M equals 2,250 divided by 350. 2,250 divided by 350 is going to be 6.4. Now here's where we got to be careful. Round to the nearest integer. If I'm at 6.4 months, can I drive the car for 7 months? No, I can't. I don't have enough money. I have enough money to drive it for 6 months, and then I'm going to have some money left over, but I don't have enough to drive it for 7 months. Is a linear model reasonable for the situation? Yes, it is. It's reasonable. The linear model is reasonable because buying a car usually consists of a down payment and constant monthly payments. The linear model is most likely not reasonable. That's not true. The linear model is most likely not reasonable. That's also not true. Okay. Moving on, 19. A motorcycle can be purchased for $9,000 or leased for a down payment of $300 and $240 per month. Find a function that describes how the cost of the lease depends on time. Okay, so the function that models this situation, I've got a $300 down payment plus $240 per month. So it says to use T right here. T is the time in months. So 300 plus 240 T. The motorcycle can be leased for how many months before the purchase price is paid? Okay. So it would cost $9,000 to purchase it. So if I say 9,000 equals 300 plus 240 T, I'm going to minus 300, and I get 8,700 equals 240 T. Now I'm going to divide by 240. So 8,700 divided by 240. You can lease the car or the motorcycle for $36.25. So you can lease it for 36 months before the purchase price is paid. At 37 months, now you're paying more than if you had just bought the motorcycle. So after 3 years, you might as well have just purchased the motorcycle. Okay, number 20. A campus Republican fundraiser offers raffle tickets for $11 each. The prize for the raffle is a $325 television, which must be purchased with the proceeds from the ticket sales. Find a function that gives the profit loss for the raffle as it varies with the number of tickets sold. How many tickets must be sold for the ticket sales to equal the cost of the prize? Okay, so our equation that we want to use, P is the profit, which equals the number of tickets that we sold. So 11, and does it say what to, and T is the number of tickets. So the number of tickets that we sold, but we have to pay for the TV, which is going to cost $325. Okay, so that's going to be my function. My profit is the amount that I make minus the amount that I'm going to spend. So to figure out the number of tickets that must be sold, we are going to, to equal the cost of the prize. So if we just want to break even, 325 equals 11T minus 325. Well, I guess if we want to break even, we don't want a profit of 325. We want a profit of 0. We're just trying to break even. So 11T has to equal 325. So if we do 325 divided by 11, that gives me 29.5. So 29.5. So round up to the nearest whole number. So if I have to sell 29.5, that means I have to sell 30 tickets in order to pay for the TV and break even. Which makes sense, right? So 21, find the degree measure of the angle that subtends the given part. So remember, to find the degree measure, we take the part of the circle, times it by 360 degrees. So 1/5 times 360 degrees is going to be 72 degrees. Find the circumference and the area. Well, circumference equals 2 times pi times the radius, or the diameter times pi. The area equals pi times r squared. So if my radius is 6, I'm going to take 2 times pi times 6. So I'm going to go 2 times pi times 6, 37.699. So that's going to be 37.699, but it wants me to round to the nearest tenth. So that's going to be 37.7, and it wants my units, inches cubed, squared, or inches. Well, this is a distance, so it's just going to be inches. My area is going to equal pi times radius, which is 6 squared, which is going to equal pi times 36, which is going to be second pi times 36, 113.097. 113.097. And I'm rounding to the nearest tenth, which is right there. So 113.1. Now I'm using area, which is inches squared, are going to be my units because I'm finding the area. 23, find the circumference and the area of the following circle. We just did that. If you need to see another one, go back and watch number 22. Number 24, a water reservoir for a city is shaped like a rectangular prism, which is that shape right there. It is 250 meters long, so this is going to be 250. It's 80 meters wide, and it has a height of 14 meters. At the end of the day, the reservoir is 60% full. How much water must be added overnight to fill it up? Okay, well, first of all, we need to know what full is. So the full amount, to find the volume, I take the length times the width times the height. So 250 times 14 times 80. So 250 times 14 times 80 gives me 280,000. So it holds 280,000 cubic, what was our units? Cubic something meters of water. But we don't need to fill it all the way up. It has 60%. We only need 40% to fill it up to full. So I'm going to take 280,000 and I'm going to times that by 40% or times that by 0.4. So if I say times 0.4, I'm going to get 112,000. So I need 112,000 cubic meters of water. So it'd be 112,000 meters cubed, or cubic meters. Suppose you magically tripled in size. I love this question. That is, your height, width, and depth increased by a factor of 3. By what factor is the amount of material required for your clothes? Well, your clothes are a two-dimensional object. So we're dealing with area. And if you remember, if we're tripling in size, then our area is increasing by that factor squared, which means we're increasing we're going to need 9 times as much clothes to cover our body. Now, if we are quintupling in size, that means we're going up by a factor of 5. By what factor is your weight increasing? Well, remember, weight is considered volume. So I have to take that 5 and raise it to the third power, which is going to be 125. So your weight, if you were to get 5 times as big, your weight would get 125 times as much. 27, convert the given degree measure into degrees, minutes, and seconds. Okay, so 36 degrees, 36.9 becomes 36 degrees. I take that 0.9 and I times it by 60 to get my minutes. So I take 0.9 and I times it by 60, and I get 54. So I would get 36 degrees, 54 minutes, and 0 seconds. Okay, same thing down here. 142.39, that's 142 degrees. I'm going to take 0.39 and times it by 60. So if I take 0.39 times it by 60, I'm going to get 23.4. Now, I don't know if we've done one of these before. This becomes 23, but I don't want that decimal. That decimal becomes my seconds. So I do 0.4 times 60. So if I do 0.4 times 60, I'm going to get 24. So that's going to become 142 degrees, 23 minutes, 24 seconds. Okay, find the latitude and longitude of the location opposite 41 degrees north, 104 degrees west. Now remember, the north, we just change to south. So the 41 degrees north becomes 41 degrees south. So our latitude is going to be south, and then our longitude, the 104 degrees west. Remember, we take 180 minus 104, and we get 76. But we have to change the west to east. So we need 41 south, 76 east. So that's going to be, where are we? 41 south, 76 east. It's going to be option C. Okay, number 30. Same thing, 33 degrees north, 105 east. The 33 degrees north opposite is going to become 33 degrees south. 105 east, we do 180 minus 105. That gives us 75, but we change the east to west. Okay, 31, find the angular size of a circular object with a 2-inch diameter viewed from a distance of 3 yards. Okay, so this one, we're going to use the formula. Our angular size equals our physical size times 360 divided by 2 pi times our distance. So my angular size equals my physical size is 2 inches times 360 divided by 2 times pi times my distance. But my distance is in yards, and I want it in inches. So I've got to take, let's see, what was it? 3 yards. And I'm going to turn that into feet. 3 times 3. 3 yards is times 3 feet. That's 9 feet. Then I'm going to turn that into inches. So I'm going to times that by 12. So 108 inches. So 2 times 360 divided by 2 times pi times 108. So 2 times 300, we better go back. 360 divided by 2 pi times our distance, which was 108. And we better make sure that we put parentheses around this one too. So 1.06. The angular size is 1.06, round to the nearest hundredth. Is that our nearest hundredth? 1.061, yeah. A planet has a diameter of 0.4 degrees and a distance of 153 million kilometers. So we're going to use the same formula, but this time we're looking for the distance, the size of the actual object. So right now it's 0.4. That's our angular measurement. We're looking for the size. That's our x. We're timesing that by 360 divided by 2 pi, and then our distance, which is 153 kilometers. So the way that I'm going to solve this is I want to move this to the other side. So I'm going to flip it over and times it by the other side. So 2 pi times 153 times 0.4, all divided by 360. So 2 pi times 153 times 0.04, all divided by 360, is 0.106. Did I miss a number? Nope, that's right. 0.106. So the true diameter of the planet, 0.106 million kilometers. Okay, I feel a lot better about that. 1.106 million kilometers, which is 1 times, let's see, we're going to do 1 times 0.06, or 1.06 times 10 to the what? 10 to the first power, just times 10, because we're moving it to the left. So 1.06 times 10 to the negative 1 and because it wants us to round to the nearest hundredth, which I think we did, right? 1.068. Oh, that's going to round to 107 because we're rounding to the nearest hundredth. 1.07 times 10 to the negative 1. And the last question, my favorite. Which of the following pairs is similar? The angles have to be the same, and it has to grow by the same amount. So these two are definitely not the same. The angles are all different. These two, the angles are all different. These two, the angles are all different. These two, the angles are the same. The shape is just a different size. So choice C would be your answer for that one.